If we look at the amount of tension a skeletal muscle can generate, we can use a machine called a myograph. And it produces something called a myogram, which is a measure of muscle twitch and tension. So over on the right, this graph here shows us a latent period. So our stimulus is going to happen right here. And then we're not going to measure anything for a short but measurable amount of time. This is the latent period where we're going to have all of the activities of excitation, contraction, coupling occur. Remember, the action potential is going to go down the sarcolemma, down the T-tubules, release calcium, and then we're going to start cross-bridging. And at that point, right here, we're actually going to be able to measure a little bit of tension. So the tension in the muscle is going to go up, and then it's going to fall off. Now, the period of relaxation is going to be longer than the period of contraction. So we've already talked about the latent period. Remember, that's all of the excitation, contraction, coupling things. The contraction is when the tension is increasing, and then relaxation is when we're kind of resetting everything in the muscle. If we do a repeated stimulation of a motor unit, remember a motor unit is all of the muscle fibers associated with a single neuron, we get a little bit of stimulation happening fairly regularly. And remember, there's a delay, and then we get a twitch, and a little more of a twitch, and a little bit more before it falls all the way off again, a little bit more, and it falls all the way off. And then we hit a region of maximum contraction. There's only so much tension that can be generated by a motor unit. So to generate more tension in the overall muscle, we're going to use a process called recruitment. So if we add more than one motor unit to our activity, then we can add the tension generated by all of those motor units. If we're going to lift up something light, then only a couple motor units might be needed, like something like a pencil. And remember, the motor units are distributed throughout the entire muscle, so no one part of the muscle is under any inordinate strain compared to any other part. If you're going to lift something heavy, you might need to engage more and more of the motor units, perhaps all of them. Now, above a certain voltage, all the units are going to be recruited, and since you're already using all of the fibers, then you're generating as much tension as you possibly can. It doesn't matter how much more you might want to contract, you're already at the maximum. There is no 110% muscles. Once you're using all of your motor units, that's it. So if you're at the gym and somebody attractive walks in and you want to bench press 800 pounds to impress them, there's just, you can't do it. So trepe is an increase in muscle twitch when the stimulations occur 10 to 20 times per second. Now, the voltage stimulation is going to be the same, and there's enough time for the muscle to completely relax after each twitch. But we're going to see a slight increase in the tension as we go along because there's insufficient time for all the calcium to be removed from the sarcolemma in between twitches. It's going to be kind of a jerky contraction, though. Now, wave summation or temporal summation, temporal is time, is if we increase our stimulus frequency to over 20 times per second. So we're not able to relax between twitches. That's going to give us something called either incomplete tetany or complete tetany or fused tetany. So here's our incomplete tetany. As our stimulus causes the muscle to contract, we generate some tension, then it starts to relax, and we stimulate it again before it has a chance to completely relax, then our tension is going to increase from that point, and we kind of jump up this way. And remember, this isn't trepe. We're not going all the way back to zero. And you'll notice down here that we're increasing the frequency of stimulations. So this is our temporal summation. Here's our incomplete tetany, And then once the frequency of stimulation is occurring frequently enough, rapidly enough, then we get a complete or fuse technique where the tension generated by the muscle is just at a constant level. Now here's another idea. This is called muscle tone. This is the resting tension in a muscle. Basically what happens is that the brain, even when a muscle is completely relaxed, say you're asleep or just sitting down, your brain is randomly test firing very small amounts of motor units in a muscle. And that keeps just a little bit of tension in the muscle at any given time. This helps the muscle to respond quickly when it needs to. And we keep switching the motor units so that none of them fatigue, but there's also hardly any motor units being used at any given time, so that there's a little bit of what we call the tone in the muscle, but the muscle's not actually going to contract. In other words, the amount of force isn't quite enough to move your limb even when there's no weight on the limb itself, because there's a little bit of weight in the limb. Of course, the bigger your muscle, the more tone you're going to have, because the more motor units are going to be firing at any given time. The motor units are bigger and are going to generate more tension. If you put your hands on somebody who is paralyzed, none of their motor units are firing, and so they don't have any muscle tone. As tension increases in a muscle, nothing is going to happen until there's enough tension to overcome the resistance of the work you are trying to do. So if we contract our muscles, and we can contract them very strongly, but it's insufficient to overcome the resistance, then the joints do not shorten. The joints don't move, the muscles don't shorten, but you're still contracting the muscle. In other words, if you put your palms of your hands together in front of your chest and push against them, the elbows aren't moving, your shoulders aren't moving, your wrists aren't moving. This is an isometric contraction. Metric is distance, iso means same, and so you're contracting the muscle, but the muscle is not changing length. And then the other type of contraction is an isotonic. Tonic is tension, so it's the same tension. So this is when the force of the muscle is enough to overcome the resistance of the load you're trying to move. And at that point, the tension of the load isn't changing, because you've generated enough force to go ahead and move that. But the muscle in this case is changing length, and it's either getting shorter, which you're probably used to thinking about. This is called a concentric contraction. Or the muscle is getting longer. This is an eccentric contraction. So I want you to imagine you've got a hold of a 20-pound barbell, or hand weight rather, dumbbell I guess, and you're applying 19 pounds of force. That's not enough to move the load. The resistance is 20 pounds, you're only applying 19. Now, your muscle is still contracted. So this is an isometric contraction at this point in time. Now, as soon as you increase the tension a little bit and meet that resistance, then the load starts to move because the muscle is going to get shorter. So as your biceps brachii gets shorter and shorter, the angle of your elbow is going to decrease and your elbow will go into flexion, and you are in a concentric contraction. The angle is getting smaller, the muscle is getting shorter. And then, because you don't want to drop the dumbbell on your foot, you gently lower it back down slowly, and that is your eccentric contraction. You are still contracting the muscle, but you're doing it in such a way that the muscle is actually lengthening as it is contracting. So here, the man holding the baby, The baby is not moving, the muscle isn't changing length, but he's still generating tension, otherwise the arm would just flop and the baby would fall. So this is an isometric contraction. And then as the man gently lowers the child down, that's going to be an isotonic contraction. And as the muscle is getting longer, that's our eccentric contraction. And as it gets shorter, that's the concentric. If you have a circle and you make smaller circles inside that circle, these are concentric circles. And if you make bigger circles around the outside, these are eccentric circles. And so that's where we get those names from. So clinically, with isometric contraction, if you do sustained isometric contraction, that's going to actually increase blood pressure. So, for instance, shoveling snow, you get a lot of peripheral constriction from the cold. So the blood is literally being squeezed out of your arms and legs just a little bit, which forces it into your torso. And since there's more of it in there, that's going to increase pressure. And then because of the isometric contraction, that also increases pressure. And it's really common for people to have heart attacks when they go out and shovel snow. I also want to talk about something called the length-tension relationship. Muscles produce different amounts of tension according to how long they are from what we would consider their normal resting length. There's kind of a sweet spot in the middle where the muscle is going to generate the most tension. And then if the muscle is elongated, if it's been stretched out, then the actin and the myosin fibers don't have very much overlap. And so there's not many myosin heads that can engage with the actin. And so there's just not a lot of tension that can be had. On the other hand, if the fibers are really short, you can generate more tension, but the movement is limited. And so it's hard to do a contraction. So basically anywhere between, about 80 and 110% or so of resting muscle length, we have our greatest amount of tension able to be generated. So again, here's where the muscle is stretched out, the sarcomeres are extended, the actin and the myosin have very, very little overlap with each other, and there's just not a lot of tension that you can generate. On the other hand, when the muscle is fully contracted, it's really hard to keep on moving. And so again, you can't generate lots of tension. And then the sweet spot, of course, is in the middle. So if you take your dumbbell and you extend your elbow all the way down and then start to lift it, it's really difficult. And it's pretty hard until you get up kind of in the middle where your elbow's at 90 degrees. And it's a lot easier at that point because you're at the normal resting length of the muscle. Now, muscle fatigue is interesting. It's the inability or the reduced ability to produce muscular tension. And it's usually because of a decrease of glycogen storage. Now, you're not running out of ATP. You don't do that until you've been dead for a couple hours. So if there's insufficient calcium because you've damaged the muscle and some of it's leaked out, if you've been using it so much that you're starting to run out of your acetylcholine, you've damaged your synaptic vesicles. If you've damaged the sarcoplasmic reticulum and you're having issues with calcium release, all of these things will cause muscle fatigue. Now, as a muscle responds to exercise, it will change over time. If you are doing more endurance exercise, then you're going to start to generate more of those oxidative fibers, and you're going to be able to do better ATP production doing oxidative phosphorylation, the Krebs cycle, with more mitochondria. If you do resistance exercise, that leads to the muscle cell getting larger as you put in more actin and myosin, so that's hypertrophy. If you don't exercise, then the muscle cells shrink, and that's atrophy. And remember, you don't lose or gain cells. The overall muscle size and the size of the cells will change. As we get older, we tend to lose muscle mass. There's a slow progression that begins in a person's mid-30s just due to decreased activity. The skeletal muscles will shrink in size, they'll decrease in power and endurance. You'll start to lose fiber diameter. You'll be able to do, you'll have a decrease in oxygen storage capacity. And any kind of injury is going to also decrease the effectiveness of a muscle. If you damage a muscle and it doesn't heal properly, you can have fibrotic scar tissue in there where you've got a lot of collagen. And collagen, remember, doesn't stretch very well, and that's going to decrease the flexibility of the muscle and also can interfere with contraction. And that's not to say that aging has to result in atrophy. It just usually does. But if you exercise throughout your life, you're able to do excellent work up until very late age. Google Jack LaLanne if you're unfamiliar with him. He was a bodybuilder and did amazing feats of strength even into his 70s and 80s. Now, if you want to get big muscles fast, you can always juice with some anabolic steroids. They're going to mimic testosterone, and they're going to increase the production of the actin and the myosin, but they can have some pretty bad side effects. The increased risk of heart disease and stroke goes up dramatically. They'll damage the kidney, they'll damage the liver, they'll cause the testes to shrink. You can even have breast development in males. Also some masculinization of females if they take steroids. Growth of facial hair and menstrual irregularities. With homeostasis, it's really not a good idea to mess with a system that's already working. Really quickly, we're going to talk about smooth muscle. So this is a complete break from our skeletal muscle. I'm not going to talk very long about it. Remember, it's found in the walls of hollow organs, such as your blood vessels, the respiratory bronchi, the intestines, the uterus, and other various locations. It's microscopically short. It's much simpler than skeletal muscle. It takes a lot longer to contract, but can sustain a contraction for a lot longer period of time. And it does not need input from the central nervous system because it is involuntary. So all your blood vessels have smooth muscle, or I shouldn't say that. Almost all your blood vessels have smooth muscle. We find it in respiratory bronchioles, the digestive system, and the urinary system with the bladder, and even in the reproductive system. Smooth muscle has a really long latent period. It also contracts for a long period of time. The calcium pumps are kind of slow. And it uses something called the latch bridge mechanism that you don't need to go into. But it's very slow to contract. It's very slow to relax. It's very fatigue resistant because of the enzymes used in it. And it can maintain a contraction without ATP through this latch bridge mechanism.